I am so glad you're here. Let's dive right into molecular representations. Specifically, let's start by looking at propane. Propane is a fuel that has a structure of CH3, CH2, CH3, and this would be a reasonable molecular formula for propane, which contains 3 carbon atoms, and 3 plus 3 plus 2 is 8 hydrogen atoms. This molecular formula, though, doesn't tell us much about the bonding or the structure of propane. For example, propane can be written like this, where you have 3 carbon atoms attached to one another through sigma bonds. The 2 outer carbons would have 3 hydrogens each, allowing carbon to be surrounded by a total of 4 atoms. Additionally, the center carbon contains 2 carbon to hydrogen sigma bonds, also giving us a total of 1, 2, 3, 4 atoms surrounding carbon. Carbon typically has 4 things surrounding it because it has a valence of 4. Its oxidation state is typically 4 plus or 4 minus, and in the neutral state, that's commonly how we're going to find carbon in organic chemistry. However, for more complicated structures that you're going to learn about in organic chemistry, writing them out like this is going to be incredibly complicated and tedious. In fact, organic chemists have developed a way to shorthand notation the way that we write these chemical structures. For example, I could convey all the same information simply by writing this, which is much easier to write than either of these other two representations. And that's because each point or vertex corresponds to a carbon atom. So here there's a carbon atom, here there's a carbon atom, and here there's a carbon atom. In addition, because carbon and hydrogen bonds are so ubiquitous in organic chemistry, we can actually omit the structure of the carbon-hydrogen bonds, and it's understood that at those places where you don't see any additional attachments or bonds to other atoms, that it must be a carbon-hydrogen bond that would satisfy the carbon being surrounded by an octet of electrons or 4 other atoms. For example, from this point to this point, there is a single sigma bond between 2 carbons. That gives us 1. That means that anytime you have a point that ends at a terminal carbon, that there must be 3 other hydrogen atoms there, just like it was drawn in this structure. However, we can omit those carbon-hydrogen bonds, and it's understood that there are 3 hydrogens here. Similarly, when 2 lines come together to form a vertex or a turn in this line structure, this lets us know that there is a carbon there, but in addition to that, there are 2 hydrogen atoms. So the 2 hydrogen atoms are here, and at each one of these points, there are 3 hydrogen atoms, giving us our full structure, which we could have drawn previously, like this. And notice still, this is also a more simple way to drawing this structure because we recognize that at each point there is a carbon atom, and at where 2 lines intersect there is also a carbon atom. Importantly, this is unique for carbon, specifically for carbon and hydrogen bonds. If we have other atoms that are present in our molecule, we typically draw those out completely. For example, oxygen or sulfur are common ones that you'll see in organic chemistry. Let's take a look at a more complicated example so we can walk through the order of operations to draw the right structures in organic chemistry. We begin by drawing the carbon chain and any atoms attached to carbon. So a way that you might do this is starting on the left-hand side and moving right. Importantly, first thing that we see is in parentheses, we see a CH3, also known as a methyl group, and we see that there's a 2 following that parentheses, indicating that there are 2 of these methyl groups, and they are going to be attached to a carbon. So we can start there. We have a carbon with 2 methyl groups, which are CH3, so we'll draw in those. And when we do that, we are beginning to form all of our structure by first drawing in those sigma bonds, which are the first bond formed in any sharing of electrons. The next thing that we see is that that carbon is attached to another carbon, which is attached to another methyl group, indicated by the parentheses, indicating that there's a CH3 group attached to that other carbon. So we can attach these 2 carbons with another sigma bond, knowing that that second carbon is attached to a methyl group. So we'll draw in our CH3, just like this. And then the next atom is an oxygen. So we'll draw in an oxygen. And that oxygen is attached to a CH2. So we'll draw in a C and then 2 H's to give us our CH2 group. Additionally, we could have drawn the CH going downwards. So instead of having it in this position, if you drew it like this would also be totally fine at this point. Then we see that the next carbon is attached to an H, as well as another methyl group, as indicated by that parentheses. So we'll draw in our C, which is attached to another H, and also that methyl group. So we can draw that in, and now we move on to the CHO. So the way that this was written would lead me to believe that this is C, followed by H, followed by O. However, importantly, something that you should remember from general chemistry is that hydrogen is one of the atoms that only needs to be surrounded by 2 electrons to satisfy the noble gas electron configuration. So for that reason, hydrogen is typically never going to make 2 bonds. So this must not be the way that this is drawn. And in fact, instead, what we can do is draw a CH bond as well as an O up here. Now we would say that that hydrogen is monovalent, meaning that it is only attached to one other thing. Remember, carbon is typically tetravalent or attached to 4 different things. So there are 4 sigma bonds going to this carbon. And now that we've drawn this framework with just sigma bonds, we can go back and check to see if each atom is surrounded by an octet of electrons. For example, in this one, we see that there are 2, 4, 6, 8 electrons because there's 2 electrons in every sigma bond. That means that this carbon fully satisfies the octet rule. Similarly, these other methyl groups are also surrounded by 4 things. There are 4 sigma bonds, making carbon tetravalent, making the hydrogens only needing to satisfy the duet, so all of those are fine. But one of the first ones that I see that do not satisfy the octet rule is going to be this carbon-to-carbon bond. Notice that each of these are only surrounded by 2, 4, 6 electrons. Similarly, for this carbon, there are 2, 4, 6 electrons coming from the 2 electrons in each of those sigma bonds. And a way that we can satisfy the octet rule is if there were a pi bond in between these. So we have a sigma bond and a pi bond adjoining these 2 carbons, giving us a full octet surrounding each of the carbons. I also see that on the other side, there's a carbon only surrounded by 2, 4, 6 electrons. So what I can do is draw in another pi bond between this carbon and oxygen, giving us a full octet surrounding this carbon. Finally, we can complete this structure by drawing in lone pairs on the oxygen atoms to give those a full octet of electrons. So we will draw 2 lone pairs on each oxygen, allowing them to satisfy the octet rule and giving us what is finally a reasonable Lewis structure of this more complicated molecule. Now let's look at some more bond line drawings and see how we draw these structures in a more shorthand notation for organic chemistry. The first example is butane, which contains 4 carbon atoms, each surrounded by a total of 4 atoms, satisfying the octet rule, mostly comprised of carbon and hydrogen bonds. Carbon atoms in a straight chain can be drawn as zigzag lines. For example, this would be the structure of butane. Remember that at each point or vertex where 2 lines adjoin, we know that there are carbon atoms. So there are 1, 2, 3, 4 carbon atoms, the same as in this structure of butane. Notice that for this fully drawn out structure, we are fully labeling all carbon and hydrogen atoms. However, for this bond line structure, we don't need to. We know that at each point or vertex, there's a carbon atom. We know that each of those satisfies the octet rule, and the invisible atoms not drawn are going to be hydrogens. So since there is a single carbon here, and it has a single sigma bond, that must mean that there must be 3 other atoms surrounding it, and in this case, those are all 3 hydrogen atoms. Similarly, for the vertex at which these 2 lines adjoin, there's a carbon atom surrounded by 1, 2 other atoms, which must mean that there must be 2 carbon and hydrogen bonds at that point. The same is true at this location, where you have 2 lines giving us 2 sigma bonds at this carbon, which must mean that there are an invisible 2 carbon-hydrogen atoms. When drawing something with double bonds, you typically want to draw them as far apart as possible. So typically, this would be the way that we would draw acetone. So this is the structure for acetone. Remember that at each point or vertex, there's a carbon atom. So we have 1, 2, 3 carbon atoms, same as in the fully drawn out Lewis structure. We will place in the lone pairs surrounding the oxygen, and we know that we don't need to draw in our hydrogens because if this carbon is attached to only one other atom through a single sigma bond, that is only 2 electrons, which means we would need 3 more hydrogen atoms to satisfy the octet rule around carbon, making it tetravalent or surrounded by 4 things. And typically this is the way you would draw this, as opposed to something like if you tried to put the double bond going downwards. Typically this is not the way that you would draw acetone. Now let's say you had a molecule like ethanol. So ethanol contains a CH3 group followed by a CH2 group, and it is attached to an OH group. We call this an alcohol functional group, and this would be the fully drawn out Lewis structure of ethanol. And the way that we would draw this when we're drawing the bond line structure is simply to be just like this. Now, noticeably, I want you to notice that because this hydrogen is not attached to carbon, we actually do need to include it here. Unlike when we have just our CHs, and in this case a CH3 and a CH2, we can omit the hydrogen, but when the hydrogen is not attached to carbon, we need to make sure to draw it in. In the previous example of ethanol, we saw our first example of what's called a functional group. So in this case, we would have some R group, which indicates some chain of carbons, either an alkyl or an aryl chain, attached to an OH group. We always call that an alcohol functional group. Additionally, if we have an R group, meaning a chain of carbons attached to a halide, indicated by the symbol X, we would call that an alkyl or an aryl halide. Additionally, if you have 2 carbon double bonds, we call that an alkene. I have a whole video here of walking through all the important functional groups that I would encourage you to check out. Now, we've talked a little bit about the fact that carbon is typically always surrounded by 4 total atoms. And while that's generally true for neutral molecules, occasionally in organic chemistry, we're going to encounter charged species, specifically either carbocations or carbanions. Carbocations contain a positive charge, indicating that you haven't satisfied the full octet rule, and in fact you're missing an electron. So for that reason, at this center carbon, where there are 3 attachments to that center carbon, the positive charge indicates that there is a lack of that 4th attachment. So for that reason, at this center location, you would not have any hydrogens. You would only have hydrogens at the terminal carbon positions at the end of each point. Similarly, remember that for butane, we would have CH3, CH2, and this would also typically be a CH2. However, the existence of this positive formal charge indicates that there is a -1 of those hydrogens. So in this case, there's only a single hydrogen here, and in fact, there's an empty orbital at this carbon position, which we indicate with this positive charge called a carbocation, because it is a cation at a carbon species. And notice that the position of the carbocation matters, because typically our terminal or point carbons are going to have 3 hydrogens surrounding them. However, because there is a positive charge here, that indicates that you're missing one, and in fact there are only 2 hydrogens at this location. Similarly, we can have carbanions that indicate a lack of an attachment to one of those 4th atoms. So in this case, we would have CH3 with 2 electrons, or a lone pair, and because of this gives carbon 1, 2, 3 plus 2 electrons gives us a total of that extra one, which is why we have a negative charge as opposed to a lack of an electron, which would give us a positive charge. When drawing Lewis structures, we need to make sure that if there is a formal charge, we indicate that so that we can account for the counting formalisms and making sure that we have the right number of carbon and hydrogens or other atoms in our structure. In bond-line structures, we need to make sure that we always include the formal charge. Otherwise, our bond-line structure is effectively useless. In contrast, lone pairs are often omitted, and it's just assumed that the correct number of lone pairs are present to give us a neutral or whatever the charged species is, which means we need to be able to figure out how many of those electrons should be present, even though they're omitted from a structure like this. For example, oxygen is in group 6A of the periodic table. It's 2 atoms away from its nearest noble gas, and we can calculate its formal charge because there are 6 valence electrons. We know that there is a +1 charge, giving us a total of 7 valence electrons, which is 1 more than oxygen normally has, being in group 6 of the periodic table. A way that you can figure out the number of valence electrons is to just start on the left-hand side of the periodic table, count until you get to that atom. In oxygen's case, it would be the 6th atom on the 2nd row of the periodic table, so in its neutral state typically has 6 valence electrons. The 1 in this scenario comes from the fact that there is a 1- formal charge. And since one of those electrons are being used to make this covalent sigma bond between carbon and oxygen, that means that we have 6 left over, which we need to place as lone pairs surrounding this atom. So even though they were omitted previously, I can figure out how many lone pairs are actually present on oxygen. Importantly though, you need to get in the habit of understanding that the same structure is this, even though we are omitting the number of lone pairs. In the case of oxygen, a single negative charge indicates that there is 1 bond and 3 lone pairs, and the exact same as in this example. For oxygen, if there are 2 bonds and 2 lone pairs, then this is a neutral atom. And if there are 3 bonds and only 1 lone pair, then in fact this is a positively charged oxygen species. And this is the most common ways that you're going to see oxygen in all of organic chemistry, with 2 bonds and 2 lone pairs being neutral, with 1 bond and 3 lone pairs being a 1- charge, and with 3 bonds and 1 lone pair being positively charged. Importantly, you are almost never going to encounter a scenario where a carbon atom would contain 5 bonds to it. This is called a Texas carbon, and in organic chemistry, you are almost never going to encounter 5 bonds to carbon. Throughout organic chemistry, you're also going to encounter molecules that contain 3-dimensional structures, and we need to indicate that by using what are called wedges and dashes. So in this case, a wedge is drawn as a shaded in bond indicating a sigma bond between carbon and chlorine in this example, and the wedge indicates that this chlorine atom is coming out at you, out at the screen. And in fact, what is invisibly written here, remember carbon and hydrogen bonds aren't written, is going to be a dashed hydrogen because the hydrogen is coming back into the screen, whereas the chlorine is going out at you, towards you from the screen. The dashed lines, again, indicate that the carbon to chlorine bond is actually going backwards or into the screen. And this is how, even though you're watching this on a two-dimensional screen, we can indicate that there is a three-dimensional structure of these molecules. Now, this is an example of an acyclic molecule, and a cyclic molecule, we can also indicate this with wedges and dashes. So in this case, the alcohol would be coming out at you towards the screen, whereas the dash indicates that the chlorine is coming backwards into the screen. Similarly, we can indicate this with fused ring systems, where if you have, for example, a 6-membered ring here, in addition to a 5-membered ring which shares atoms, we would draw in the wedge for the 5-membered portion to indicate that this is a 5-membered ring that is fused to a 6-membered ring. And here you also see a wedge for this alkyl bromide and a dash for the methyl group. Now, importantly, remember that at each turn, that indicates a carbon. Carbon needs to be surrounded by 4 things. So if this dash chlorine is coming back at you, that means that invisibly there's a wedge indicating that a carbon hydrogen is coming out at you from the screen. Now let's try some practice problems to gauge your understanding. Importantly, I would encourage you to pause the video, try these problems independently, and then you can resume the video to check your answers. We can simplify the structure of vitamin C by using the bond line notation that we learned about in this video, specifically knowing that I can omit the presence of carbon and hydrogen bonds by knowing that at each point or at each turn there's a carbon atom. So where there is a carbon to oxygen double bond at this position, I don't need to draw in the carbon because I know that at this point there is a carbon at the center of it. So for the next carbon, I can just draw in my OH alcohol group and I can turn to go to the alkene. By simply drawing in these 2 lines between these 2 points, I know that there is a carbon at the end of each of those. So then when completing the 5-membered ring, all I need to do is align those points indicating that there's a carbon here. Now I can go in and draw in my other alcohol at this position, matching this side. From here, even though there is a carbon to hydrogen bond, I don't need to indicate it because I know that at this point, this carbon, since it's neutral, needs to be surrounded by 4 atoms. So even though there are 1, 2, 3 bonds, I can omit that carbon to hydrogen bond and it's just assumed to be there. At this point, I need to draw in my other alcohol, but again, I don't need to draw in this carbon hydrogen bond because I know that there are 1, 2, 3 bonds attached to carbon, and invisibly there's a hydrogen atom there as well. And then for the last piece, that's all I need to draw is that point because there is a single carbon there, and since it's neutral, it must be surrounded by 3 other carbon to hydrogen atoms, giving us a full octet. Now when going back in to draw the lone pairs, none of the carbons or hydrogens need lone pairs, but the oxygens do. So oxygen typically has 2 bonds to it and 2 lone pairs in its neutral state. So for that reason, we can place a lone pair here and a lone pair here, giving us a full octet since there is 2 electrons between the covalent bond of oxygen and hydrogen and 2 electrons between the covalent bond between oxygen and carbon. Similarly, at this carbonyl carbon position, there are also 2 lone pairs. And at this ether position, there are also 2 lone pairs. And then finally, for each of the alcohols, there are also 2 lone pairs because each of these oxygens contain 2 bonds and 2 lone pairs satisfying the octet rule. Remember that in the neutral state, most atoms need to satisfy the octet rule. The way that we can calculate formal charge can be done by remembering that the number of valence electrons minus the number of bonds surrounding that atom minus the number of lone pair electrons will give us the formal charge. So oxygen is the 6th element on the 2nd row of the periodic table, so therefore it has 6 valence electrons. In this molecule, there are 1, 2, 3 bonds surrounding oxygen, and there are 2 electrons as a lone pair also, giving us 6 minus 3, which is 3, minus 2, which is equal to 1. And since this is a positive 1, that means that we need to place a positive formal charge on this oxygen atom. We can do the same thing for this molecule if we recall that the nitrogen atom is the 5th element directly adjacent to oxygen on the periodic table, meaning that it has 5 valence electrons. There are 1, 2 bonds surrounding nitrogen, and there are 2, 4 lone pair electrons. Therefore, there's 5 minus 2, which is 3, Minus 4 gives us a negative 1, and for that reason, this nitrogen should have a minus formal charge around it. And using this formula is a quick and easy way to calculate the formal charge of a molecule. For example, we can also do the same for carbon. So if we recall, carbon is the fourth element on the second row of the periodic table. So therefore it has 4 valence electrons. There are 1, 2, 3, 4 bonds around it, and no lone pair electrons. Therefore, the formal charge of carbon is 0. If you enjoyed today's video, make sure to subscribe to my channel for more content. Additionally, I would encourage you to check out this playlist, which contains all the sequence of organic chemistry, including Organic Chemistry 2. Until next time, I'll see you in the next video.